Good morning, wonderful earth science kids. Today we're going to be talking about metamorphic rocks and how it all works there. In the first picture here, you see uh, some idea of uh, the things that can happen that would make metamorphic rock. If you look at this lava pool right here, well, what's that going to do to rock around it? It'll burn it, and that can make one type of metamorphic rock called hornfels. Um, In the other situation here, you see what happens under extreme depth. Tremendous pressure squishes things and can change how things are. So both of those things can create metamorphic rock. Metamorphic is rooted in Greek, which means to change shape. Meta meaning to change, morph meaning form, to change shape. So metamorphic rocks form from other rocks that undergo intense heat and pressure, but not melting. This causes them to, and this is an important word for metamorphic, recrystallize, which means to form new minerals. Metamorphic rocks are rocks that have morphed into another kind of rock. These rocks were once igneous or sedimentary rocks. How do the sedimentary and igneous rocks change? Well, the rocks are under tons and tons of pressure, which fosters heat buildup, and this can cause them to change. If you examine metamorphic rock samples closely, you'll discover how flattened some of the grains of the rock are. The Earth is dynamic. The picture you see here shows some of the processes of plate tectonics, and that's constantly squeezing the Earth rocks together in ways that can start them to recrystallize and form those new minerals. It takes a lot of heat and pressure in order to get this to happen. Recognize that all rocks are under a fair amount of heat and pressure to begin with, but they're not recrystallizing. It's the recrystallization that is needed. These rocks are physically deformed and chemically changed due to different temperatures and pressures. The elements in the minerals can actually move to form new minerals. The rock does not melt, or else it would be considered an igneous rock. The rock looks very different after it has been metamorphosed. The rock's texture and overall appearance changes also. It now has a squished look. Take a look at that rock there. You could see all sorts of funny lines running across it. How would a rock ever end up looking like that? Needs a lot of heat and pressure. There are two types of metamorphism. One is regional, where the heat and pressure is applied to large areas of rock in the collision zones of the Earth's tectonic plates. So here would be an example of that. And if we look at the areas here where you have different plates being squished together, right along this area here, you have such intense heat and pressure that you can cause large areas to become metamorphic rock. Very large areas when it's regional metamorphism. You can have whole states turned into metamorphic rock. After all, if you look at the Vermont license plate, it's called the Green Mountain State. Well, doesn't don't most Northeast states have nice green mountains in the summertime? Sure, but that's not what they're talking about. In Vermont, the rock underneath them is a rock known as schist, and it's a greenish looking rock. That's why they call it the Green Mountain State. The other kind of metamorphism is contact metamorphism, where the rock is burned due to heat from the lava or magma. So you can have a large intrusion and it will burn the rock around it. Not a great deal of rock, a couple 100 feet sometimes if it's a huge intrusion. And if it's a very small intrusion, it will only burn a couple centimeters around it, not so much. So the contact metamorphism is not nearly as important as the regional metamorphism. It's sort of hard to find contact metamorphic rock, and they don't look really like much. But the regional metamorphic rock, well, now that's something. So some types of metamorphic rock to pick up and actually look at. Foliated, have banded, striped, or layered minerals due to pressure applied during the metamorphism. So if you take a look at this rock, all right, this rock has a shiny appearance, it has a flaky appearance. You can actually get flakes to come off of this. And it's mica. So this would be a foliated rock, an example of that. This would be another one. This is that beautiful schist. And it looks like a bunch of oatmeal, green oatmeal grains, tightly cemented together. This is slate and also has a layered appearance to it. Well, the one thing these layered rocks all have in common, this is gneiss. Notice the banding on the gneiss. The one thing they all have in common, they're all made from clay. Clay, there's so much clay made when a mountain breaks down. The mountain basically mostly turns into clay. What doesn't turn into clay turns into sand. So whatever happens to clay is going to be really important. Clay first turns to this rock, shale, right? In the Catskills, we have tons of shale around us. Well, any place where shale gets metamorphosed, the shale becomes slate. Slate becomes another rock called phyllite, sort of an in-between rock. The phyllite then can become schist, and this is all as you expose it to more heat and pressure. The schist can become gneiss. If you expose it to more heat and pressure than that, it's going to melt and become an igneous rock. It's as much heat and pressure as a rock can take without melting. So those are all the foliated rocks. They all come from clay. The non-foliated rocks, these are rocks that come from other source rocks. For example, this sandstone would turn into this quartzite. Right? The quartzite, the quartz grains are all interconnected here. This is a very durable, very strong rock, quartzite. If you have marble, I'm sorry, if you have limestone, limestone will become marble, a beautiful rock that sculptors have used for centuries to make our statues. So there's no lines or bands in these. They're just previous kinds of rock that were changed. This is known as metaconglomerate. A conglomerate exposed to heat and pressure, everything welds together. So those are the two major kinds of metamorphic rock. Foliated, which have layers or bands on them, and non-foliated, which don't have anything like that. So this is some schists and some gneisses. These are common in New York City and Westchester County. Beautiful things. Why New York City and Westchester County? Well, aren't they closer to the edge of the continent? And it's the edge of the continent where all the action has happened when the ocean previously has closed up and crashed. We have lots of evidence that all this stuff has occurred. So you have a quartz sandstone where the quartz grains are separate, and when you expose that to heat and pressure, the quartz grains intergrow with each other, and they'll turn into quartzite, this beautiful crystalline quartz. It's lovely stuff. So you start with shale, and then you hit it with pressure and heat. That shale will become slate. Okay, that slate, different from shale. Shale breaks up. Heck, you could take pieces of shale and crush them in your hand sometime. Slate, no, you'll never be able to do that. A thin piece of slate is really quite durable, used for porch stones and things like that. The slate, hit with more heat and pressure, turns into something called phyllite. Phyllite is a little bit shinier, sort of midway between slate and the next rock, which is schist. Schist is green, shiny, flaky crystals generally. And after that, you hit that with heat and pressure, and you can end up with gneiss. Gneiss is alternating light and dark bands. In every case here, you see alternating light and dark bands. Look at this rock. Everywhere here, you see light band, dark band, light band, dark band. Same with this, light band, dark band, one after another. That is absolutely what gneiss is. Gneiss is alternating light and dark bands, and it is the most intensely metamorphosed that you can make this rock. If we take a look at some metaconglomerate, if you look at typical conglomerate pieces here. If you expose that to heat and pressure, you're going to get a wild-looking rock. Look at this, where you have all these pieces that were once pebbles. First of all, it's all welded together. You can't break any of this apart. And the pebbles get a flattened, squished look to them. Definitely increases its density and turns into an interesting rock, metaconglomerate. So here's limestone. And if you expose limestone to heat and pressure, it turns into the beautiful rock called marble. It's what we make all our statues out of. This igneous rock, gabbro, when you metamorphose it, check out this rock. That's some wild stuff. Green schist. It's utterly bizarre. Makes beautiful building stone. Some features you'll find in metamorphic rocks. Well, sometimes they have a banded, striped, or layered appearance. That would be that foliation. They can enlarge mineral grains and create entirely new minerals. Very often you'll have large grains of garnet grow in the rocks. There's a variety of really pretty rocks that you can form this way. But the minerals, they tend to grow larger just because the elements can move around inside the rock, so they move to their most favorable positions. Metamorphism will definitely increase the density of a rock. It's just squishing everything together. And a lot of times it'll make this distorted or twisted rock structure by this intense pressure. So look at the scheme for metamorphic rock identification. And you can see, first of all, we break it up into foliated and non-foliated. Remember, foliated, this is everything that happens to clay. All right? So when we start, notice low-grade metamorphism of shale makes slate. As you increase the heat and pressure, notice it goes down. So slate turns into phyllite, turns into schist, turns into gneiss. What happens if you hit it with more heat and pressure? Well, it melts. So that's as far as you could go with that. Down here, the non-foliated, these are what happens to different pre-existing rocks when you hit them with heat and pressure. So if you have bituminous coal, it turns into anthracite coal. If you have contact metamorphism, remember when you're touching a lava tube or a magma chamber, you just generally group all of that into hornfells, but you can also call it the equivalent of whatever it would have turned into. In other words, if it's sandstone, instead of calling it hornfells, you might call it quartzite. If it's limestone, you might call it marble. If it's conglomerate, you might call it metaconglomerate. Hornfells would be just for contact metamorphism, so there's obviously multiple names you can call it. Contact metamorphism, yes, it's hornfells, but it would also be able to be called whatever it would be under the other scheme. So sandstone to quartzite, limestone to marble, coal to anthracite coal. So this gives you the whole scheme for it. Notice on the top here, they might ask you what minerals you're passing through. So slate, what kind of minerals are in slate? Well, just this, mica. When you get to phyllite, now look at all the minerals that you're starting to grow. By the time you get to gneiss, you're even growing pyroxene through that too. So these would be all the minerals you will tend to get in metamorphic rock. That is wild. I hope at this point you'd have no question that that is clearly a metamorphic rock. And what kind of rock would that be? Nice. What kind of rock is that? Sure enough, alternating light and dark bands, that's an exposure of metamorphic rock. And that would be nice. We remember the rock cycle. Rocks constantly are changing at the Earth's surface as they experience different conditions. So let's look at what it takes for any rock, about an igneous rock, to come over and be a metamorphic rock, right? Well, look at the words. Heat and or pressure, metamorphism. What's the word missing there? Recrystallization. That word is not there, but that's a word you need to know. So sedimentary rock, what does it take? Heat and or pressure. So any one kind of rock can go back and change to different kinds of rock. Just use this to determine what the words would be. Thanks for watching.